Hello guys, welcome to part 4 of 2.2 Equilibrium and Yield. In this video, we'll be focusing on the second table, which is on slide number 3, especially the change that you can make, so concentration, overall pressure if it's a gaseous mixture, and also temperature of equilibrium mixture. We'll also look at the graphical representation of those changes and how equilibrium position shifts. All right, we're going to jump on to the example that you can see on slide 22. So slide 22 is about change of concentration. So picture this, you've got a system, a chemical reaction that has reached to the equilibrium, and now you are changing concentration of either reactant or product. So in this example, you've got 3 gases, so 2 reactants, which are carbon monoxide gas, and CO2, which is chlorine gas, and from that you can get COCl2. Don't know what's that called. But yeah, CO2 is what you get as a product, and you can see that it can form equilibrium, two-way reaction. Okay. Now, addition of CO2 or CO, which is reactant to the system, results in an increase in concentration of reactants. So that's the external change that we are looking at. What's going to happen after that? The equilibrium will shift to the product side. Why? Reducing the concentration of the reactants, which is number 2, is what the system wants to do, okay? Which increases the concentration of the products eventually, and this occurs to counteract the increase in reactants until a new equilibrium is reached. There's a note there. This reverse is also true. So if you change the if you increase the what change would happen if the product was added? So if you have got a system that reached to equilibrium, and if you added some CO2 gas, what's going to happen? Well, I hope you are thinking about if you increase the product, yeah, it will try to reduce it. By reducing it, what's going to happen is you will get more reactant. Please note there that some of the added reactant or product is used up when the system counteracts the change, but not all of the added substance is used. Thus, the system never returns to its initial state, but reaches a new point of equilibrium. Let's look at that in a graphical manner. Now I've got different equation here. So I've got 2x and y. So 2:1 ratio, and so far twice the amount of reactants used up compared to y that's being formed. Okay, so y is the product here, and yeah, twice the amount of change compared to y. That's where we are at. You can also look at the graph and tell how the reaction occurs in terms of ratio. Okay, now let's increase the amount of product this time. So product is y, that's the red one. If I increase at T2, time number 2, by this much, what do you think would occur after that? Well, because that's a product, it will be, that's going to be consumed, because that wants to go back that way. So 2x should also start increasing from this point, T2, shouldn't it? Because that's happening, not that much. There will be a slight decrease. And at T3, I'm going to call that reached to a new equilibrium. Notice that not everything that was added is used up. There's a bit of gap there. The final line is a bit higher. What does that mean for x again. Because y is going to be consumed a bit, x should be also increasing. Yeah. If changes about this much, I want to end up about twice the amount. Now, it's not sudden change for T2. It's because you didn't add that. What you added was the sudden amount. What I made sure here was that the change from there to there is twice the amount of change that you saw here. That's about 1 here, and that being about 2. 1 to 2 ratio. Why is my 1 so small? Yeah, so that's something that you would see if you are tracking the change. We'll look at the other 2 graphs here. Okay. All right. Change of pressure / volume. Same equation there. There's an example. I'm not sure if that link is actually working, but anyway, let's look at this example here. CO plus CO2. So there are 2 moles on the reactant side, and you've got CO2, which is 1 mole, 2 to 1 ratio. Yeah. If the pressure is decreased, or you could say that the vessels expanded, so there's more room available. What's going to happen? The system will try to adjust to increase the pressures, because if you decrease the pressure, all of a sudden, what's going to happen is, okay, well, we need to kind of maintain the same sort of pressure that we had before. Therefore, as a result, equilibrium will shift to the side with the greater number of moles. Okay, i.e., in this case, the reactant side. This occurs as the molecules of gas in the same volume result in higher pressure. Because you decrease the pressure as you opened up more room for them, more molecules want to occupy the room that's kind of empty in order to increase the pressure again, because that's the counteracting of what you did as an external change. Reverse is also true. So how does it change? If you increase the pressure, system want to decrease the pressure. Therefore, the equilibrium will shift to the side with the lower number of moles. In this case, it's the product side. So that's what will happen. Please note there, see some systems have equal number of moles on the reactant and product side, and hence they will not be influenced by the change in pressure. Now, let's look at how that looks like. This one. How that looks like if you are tracking the concentration of reactant and the product if you changed the pressure. Let's decrease the pressure. Hang on, let's do the other way around. Let's increase the pressure. So if you increase the pressure after this system have reached to its equilibrium, if you increase the pressure, what's going to happen is because you are compressing the volume, vessel, the volume should increase straight away. By how much? Well, you can still keep the ratio here. 2x is going to be moving twice as much compared to y. Pressure increase at T2. How is it going to change again? Well, because the equilibrium this system has got twice more amount of X, and because you increase the pressure, this system wants to decrease the pressure by shifting the equilibrium to the less number of moles. So more Y would be created compared to X. So from this point, Y will increase and reaches to the equilibrium. X, on the other hand, is consumed because Y is being formed. How much? If this was a change of 1, I would like to move it by maybe around to here. Start with steeper slope because reaction is much faster at here, and then slows down to totally flat line. So the new equilibrium is established. Again, what I made sure was that the distance from here to here and distance from here to here, because that's where we started, is about 1:2 ratio. Again, sorry about the focus. I forgot to turn it off. So yeah, 1:2 ratio is what we are using. Okay, so that's for the pressure change that you applied. Okay. Next, final one, change of temperature. So, the last two, which you should add a note, go back and add a note, say that the Kc value are not affected by the change of pressure and also concentration change that we made. Kc value do not get affected unless you change the temperature. I hope you remember that the Kc stays the same as long as you keep the temperature as constant. Okay, so closed system also meant that the Kc value, temperature is constant. Okay, if you change the temperature of the vessel, the system I should say, Kc value change. Okay, now consider a different reaction here. You have got H2 gas and I2 gas. That says 2Hi, and also the new thing that's added there, delta H value. Delta H equals positive 10.9 kilojoules. I suppose this is per mole as well. 10.9. Now, 10.9, the value itself is not so important. What's important is the sign that's in front of it. You see the positive sign, plus sign. That's something that you need to make note of. What does that mean again if the delta H value is positive? That was probably mentioned in part 2 of this 2.2 lecture video series. Plus sign there means delta H is positive, and it means it's endothermic reaction. So as that reaction occurs, or as the reaction progresses to the product side, energy is being absorbed by the reaction. What does that mean? If this reaction is endothermic, which means that the forward reaction absorbs energy. Okay. If there's an increase in temperature, i.e. increase in energy within the system, then the system will counteract the change by lowering the temperature. Okay, lowering the temperature. Now, what does that mean for the reaction itself? As the forward reaction absorbs energy, the equilibrium will shift to the product side. Conversely, a decrease in temperature would favor the exothermic reaction, i.e. the equilibrium will shift to the reactant side. So picture this. So remember the container sort of example, 10 people in there and you are all crammed in there, and you are try to get away from the heat. So that also means that the couple forming in that sense was exothermic reaction, exothermic reaction. So as the couples form, heat is generated. That's how couples happen in the container. But if the external change, so container itself was heated up, what do you want to do? Well, the heat generation is no longer necessary. Because it generates heat as you come to a couple, you want to get away from each other. That's sort of the reaction that we are talking about. Okay. What's important here is that which way the delta change will happen. If it was an endothermic reaction, and if you add heat, heat kind of acts like a reactant as well, or something that speeds up the reaction, because energy is being absorbed by the reaction. Conversely, if you are dealing with an exothermic reaction, what's going to happen? Exothermic reaction exerts heat as product. So if you add heat to it, the heat dissipation becomes kind of slower. So the reaction wouldn't go as fast, and hence the equilibrium will shift to the reactant side, because heat is being now needs to be absorbed, if that makes sense. On the next slide, a bit of summary there. If a reaction is endothermic, which means delta H is more than 0, positive sign should be used. Decreasing the temperature favors reactant. Therefore, increased temperature favors product. Yeah. If the reaction is exothermic, i.e. delta H value is less than 0, negative sign is being used. Decreasing temperature favors the product, because reaction creates heat. So if you take the heat away, the reaction would go forward. Increase the temperature favors reactants conversingly. There are questions that you need to do there, but before then, let me just talk about this summary as well. Oh, before then, I should talk about graphs, how they look like. So, wait to focus a bit. All right, now we were looking at this reaction again. Let's start from here. Now, I didn't really talk about the delta H here, but let's say that delta H here equals to, shall we go? Negative. Well, just say that. It's less than 0 here. Okay, so forward reaction is less than 0, so exothermic. This reaction generates heat as you go to the right. That's the context. What's going to happen if you change the temperature at T2? Shall we also then increase the temperature? So add heat at time 2. Add heat at time 2. Which way does any reaction would like to react to? If you're adding heat, the system will prefer endothermic direction. So, which one is endothermic reaction again? It's going that way, because the going right is exothermic direction, so endothermic will be to the left. So we should see a bit more of X being created and less of Y would be observed. Now that reaction does not occur, so you shouldn't like jump like that. What you should do instead is something like that, flat. So new equilibrium is again achieved at T3, EQ2 was achieved at this point. Okay. If this increased, something must be consumed. So Y is consumed, and it can reach the equilibrium. That's something that you should picture. Maybe not so steep there because it looks too flat there. Like that. Okay. What I also again made sure was the change in distance here. So from original equilibrium to next the new equilibrium, I made sure that that's kind of like 1, 2, 2 ratio. Okay. Temperature change and the response to the external temperature change is a bit more mellow compared to sudden pressure change or sudden concentration change, because you're literally, I guess, pouring liquid or gas. In this case, it's gas, I suppose. So that's where we are. Now, all these are summarized into one table very conveniently on Essentials page 133. So I suggest you copy that from Essentials book and try doing all the questions. I hope you can also watch some, further explanations from those links that's in there. Okay, and a crash course equilibrium. If you needed further explanation, I suggest you watch that too. I believe that's the last slide. So after copying the table, do those questions up to the end of 2.2. All right, that's it. See you in the next subchapter 2.3 videos. All right.